Hello everyone, I welcome you to data science class. The topic for today is multiple linear regression analysis with visualization in Python. This is continuation of the last lecture on linear regression. I call that one simple linear regression. This is multiple linear. The difference between this multiple linear and simple linear regression is that your response variable here is 1, but predictors are more than 1. We are dealing with more than one predictor, that is independent variable. So we can look at this model equation. You have y equals beta naught plus beta 1 x1 plus beta 2 x2, like that up to bn xn. So you can see this is the difference between multiple linear regression and simple linear regression. So anytime you want to find more than one independent variable as predictors, you want to see the effect of more than one independent variables on a single dependent variable, you talk about multiple linear regression. Now the relationship is that they are both linear, and this is the definition of all these variables here. You can see x1, x2, x1 to xn in predictors or independent variable. They are also known as regressors. Then the beta naught is the intercept, where the you also have the error terms. Then already you must have installed these libraries. You must have installed the libraries. And the libraries, the pandas to import your data, numpy to do some mathematical and statistical analysis. And you see the way I'm going to do. The difference between this and simple linear regression is just what I've told you. You have two, you can see 3 independent variables here. So we are using 3 here, but the first one of them will be the response variable, other two will be independent variable. So this is an example. We want to predict height based on weight and age of certain number of students or individuals. We want to predict height. It means your height depends on weight and age. We are not going to use of their names for now. Now to run this, your df is that's the data frame representing the table. We all know this. The data frame here is to bring these variables together in the data frame. Then you print it. Let me run it. So when you run this, you can see the results. This is the data frame. So you can see the name. This is the string, and these are the one you want to work upon. Now the script strategy, I normally say that the first thing that comes to your mind you should do is to describe your data before you even go into inferential statistics, talking about p-value, talking about visualization and all the rest. Describe your data first. So now you want to print the statistics. This /n descriptive statistics, what it's doing is just that you want the result of your description of your data to have a heading, and this is the heading now, descriptive statistics. This /n you see here is to give space before writing this out. Describe is the function that gives you the summary of your statistics. We call it summary statistics. Then start model.api as sm. This one is the one we use for advanced statistical analysis. scikit-learn is from machine learning. And in my previous video, I explained what this one means. So you can use linear regression, you can use the other one also to obtain the same thing. So the scikit-learn metrics is talking about mean square error. After you have designed your model, you need to know you need to evaluate your model. How do you evaluate your model? Once the mean square error is very, very low, the value is very, very low, then we know it's a good model. The R square ranges between 0 and 1. The closer to 1, the better your model. So now I normally tell my students, if your model is good, you need to evaluate it. And if it's not good, you have to look for what to do about it. Then you prepare the independent variable. You know you have 3 variables here, 4 variables, and they are all in one single data frame. You need to isolate. You need to instruct Python where to pick which one is your response variable, which one are your. So that's what I'm trying to do here. You can see capital X is the df. Look at it now. I've defined it. My X is my independent variable. My Y is my, so weight and age are independent. I've defined them here. So whenever I'm going to use my independent variable, I'm not going to write weight and age again. I will only write X. And the reason why I use uppercase of X here is because it's a vector. I have more than one variable. I have weight and age. Though if you use small letter, nobody will query you for that. Then let me run it for us to see what I'm talking about. So it has run it because I didn't want to, I've not asked Python to show me the result. That's why it's there. Now we have the descriptive. The one I describe on top here is what I see here. You can see for the three variables. For the three variables, you have count. How many is 9? For weight, all of them like that. Then the mean of weight is this. The mean of age is this. The mean of height is this. Now for doubting Thomases, see how do we get 9? How do we get that? Just come back here. Python always start the counting with 0. That means when you have 8, it means it's 9 rows. You can see 0, 1, 2 up to 8. Then we now go to the real modeling using start model. So from this place, you can see the SMR constant. What this one does, it will give us the stochastic. You know we have betas. We have beta, that's constant. So if I don't do this, there won't be equation of straight line like you see here. Let me take you back to it. This equation. So that line of code will execute this beta naught. It will give it to us because it has to be there. Without it, your equation, your model will not be complete. Then the model SMOLS. OLS is ordinary least square, just like we did it for simple linear regression. If you have not watched that video on simple linear regression, go back. It's on YouTube. They're on the same channel. Now this start model summary. This is what I want as the heading of my result. It's not compulsory you use this. You may not even use print. Your result will come out. I only want to make my output look neater. That's why I put it there. Let me run it. See what I'm talking about. This is start model. You can see what I wrote here. You can see there's a space here. There's a space between my the heading and the result. Let me remove this N. See what I'm talking about. See, this space has come up. But I want it to go down. Let me restore it. Run. I see the space now. If I remove the space here, run it. I see. So if I remove the two spaces, run. So you can see the differences. So it's good to make your work look neat. Now you can run it. It creates space. Create space before, that space after. Now, how do we interpret this? The dependent variable is height. The dependent variable is height. The model is OLS. That's ordinary least square. Method is least squares. Date is 20th July 2025. This is the time. This is now observation 9. Now residual is this. Then look at it. The most important thing here is your R square and your p-value. Look at it, 0.988. That means your model can explain 98.8% of the variation in the response variable. You get it? 98.8% of the variation in the response variable is explained by the model. This is a good model. It means it has a very good predictive power. It can be used to predict, your height. Because your height should be predicted with your model. And look at the p-value. The p-value here is very, very low. 0.00000. You can see 17. So you are rejecting each note here. Look at the AIC and BIC, they are very, very low. Now you can see the model here. If you want to write this one out as your model equation, you just say y equals, your y is your height, is equal to the constant 26.7 plus 4.86 width plus 10.06 each. Then look at their but look at the p-value for each of them. None of them is significant. Individually they are not significant, but overall model is significant. So that's good. Now to use the scikit-learn from regression, we are still going to do the same thing. You can see where I use SM the other time, I'm now using Multiple Linear Regression. This is the function that comes from scikit-learn. You know, in this modern day when we are doing data science, we have machine learning, and linear regression is part of the function we use. So that's what I'm using here. I'm using different methods to achieve the same thing. Now this is the prediction. To predict, model sk.predict. You can see predict, the model is this. I can call this one anything, I can put my name here, but I must put predict here. The one that give me the predicted value of my y from x. Don't forget my x has been defined as a weight and age. Then the metrics. Metrics as what they are the statistics we use to evaluate our model. I've said it. The MSE is the mean square error. The RMSE is the root mean square error. Root mean square error itself doesn't have a function in Python, but it is very easy. Once you have obtained your MSE, you only need to take the square root, and you are going to get the result. Then R square, the R square score is a function. But if you use this method, the OLS method I use here, the SMOLS I use here, it doesn't have the error metrics. That's why machine learning, is good when you are dealing with such analysis here, because they have their function. You only need to apply them straight. Then now, this is the end of the road for this analysis here, but for us to have the result well presented, you can now use print. Now you can see this is going to be just the way I did it right time. This one will not create space between these outputs. Scikit-learn outputs will be the heading. Then the result will now follow. The first result will be the intercept here. You're going to create. The other method I use, I wrote this to calculate the intercept, the constant. But here this is the function we are going to use. So the intercept will come out. Then this coefficient, the coefficients are the betas. Beta 0, beta 1, beta 2. Then the MSE, you can see mean square error. Now this is going to be the heading here, followed by the MSE. MSE dot 2f. This 2f is 2 decimal places. If I put 3, it's going to be 3 decimal places. Instead of having long values. Now this one is 4 decimal places. Not significant figures. Decimal places. So this R square, this root MSE, and this. So let me run this. If it's correct, it's going to give me the result. Can you see the outputs? The intercept is this, very long. I didn't write anything in front of intercept. Okay. If I put dots 2f there, it's going to give me, it's going to summarize this, it's going to change this one to, it's going to approximate it to round it up to maybe 2 decimal places or 3, depends on what I want. Now, these are the results. Now look at the mean square error, 2.52 is not big. It's not a big value. So, and the lower this one, the better your model. Well, we are looking for cases where you're going to have 0 point something. But this 2.52 is not bad. Now root MSE is 1.5. Then look at R square. This is a very good model, 0.9881. Compare this result with the first one I did here. You see, 0.9881, the same thing. So irrespective of the method you are using, if you are using Excel, you must get the same result. Now, this is one to compare the predicted and actual. Look at the way I put it here. You can use any method you like, but it's always very, very easy. The actual y, which is the height, and the predicted y, must not be too far away from one another, from each other. And the error, you see, when you design a model, the important thing is that you should be able to use the model to predict the existing the actual values. So if you are getting 4, if 4 is in the actual value, in the actual data, and your model is predicting 10, you should know that that model may not be okay. So that's why I deem it fit that this should be done. Compare the actual and predicted. Though we know this model is good though, because the mean square error is very low, the R square is high, but we need to show it. If you are doing presentation, look at it. I've been doing this for long. I like showing this because this is a clear picture of what everything I've done. Look at actual is 50. Look at predicted 48. Look at the error. The error is just removing your predicted from your actual or vice versa. Look at it, 1 point something. So, and the assumption is that the error is normally distributed. The variance should be very close to 1 and the mean should be very, very close to 0. That's normality assumption. Compare this actual with predicted. Remove predicted from actual. The remainder is what we call residual or error. And the distribution of your error must be normal. So now we have come to the end of this. But for us to just see visualization of what you have done, because when you are doing presentation, I normally tell students they must combine with chart, graph, visualization of what you have done. This is what some people are looking for. Now let me quickly explain before I end this class. Now import this matplotlib is a library that is solely for making plots. There's one we call seaborn. Seaborn is more complex than this, but matplotlib is mostly used, and it's also in MATLAB. We have matplotlib in MATLAB. So you can see the PLT that I imported it with. If I use my name here, I'm going to be using my name here also, true, but I'm using PLT. So PLT.figure. PLT.figure. So the figure size is here 8 and 5. That's the figure size. Now we are talking about inches here. Yeah, inches. Then the plot, the name here. You can see the name. We have, let me take you back to the data. If you look at the data, we have name here. These are the names of the individual we use for this analysis. So you can see it's Olu that has the first row, followed by Ade, followed by Oda, and the last person here is Afusat. So we want to plot their values against their names. You can see. So that's what I'm trying to do here. Then their name, we want to see the predicted and the actual. Also, this one has the actual. This one we now have predicted with different marker. Because if you use the same marker, what do I mean by the marker? Those shape on the line. We want to plot actual and predicted together. We see that they will not be too far away from each other because of this value. These ones, they are not too far away. Now, the title actual versus this is very important. Though recently the journals do not accept in our papers to put our titles on top. The title of your figures on top. It's only in table that allows. When it's come to figure, that's what predicting under. So now the X label, that is the name. Horizontal axis you have name here. But Y axis, Y label is height. Then the ticks you see here, it's one of those things that you want. If you want it to be 45 people here, if you want it to be other way around, you can change it. Legend is the line behind the chart, those square lines, just to beautify it. Then the grid line, the legend are the names. The names where you will have predicted, we have actual. So that's what legend is doing. Is where you define all of those things you have shown on your charts. Then the grid line are the lines behind it, all those square lines. If I put false here, it will not show. So the layouts, how you want it to show, then you run it. Yes, you can see this actually, this is the work of legend. You can see this is the axis, the chart title. So this is axis label. Axis label, the name. You can see the one you see at the back, all those lines, they are the grid line. The one you can see this blue. The blue is actual for the height, and the red is predicted. This is a very beautiful chart. This is good for presentation. So you can see a lot of things here. A lot of things. You can interpret the height using the name of each of these values. The owner, Ulu 50. It's 50, but look at what is predicted for Ulu. Ade is around 55. Look at what is predicted for him or her, and so on. That's all. If you have any question, you can drop it in the comment side of the this video on my YouTube channel. So the next class, before the next class, try and go through and practice using your own example. Thank you. God bless you.